Good? So it's flashing red? Okay. Yes? Yes, okay, all right, so we're good to go. So just to recap what we did, we defined this function that's the integral from 1 to x of 1 over t dt. So it's the area under the reciprocal curve. And we found some properties of that function. L of 1 is 0. The derivative, first derivative is positive, so it's always increasing. Second derivative is negative, so it's concave down. And we're defining it for x greater than 0. So putting all that information together, we figured out that the graph has to look like this, and that the limit as x approaches 0 from the right is negative infinity. So this function, L of x, has several other interesting properties that we're going to derive using this integral definition. And it will start to look familiar, like maybe some other functions that you've seen before. So we'll do that over here. First thing I want to figure out is what happens if you take L of 1 over b. So like if you knew what L of 5 was, could you figure out L of 1/5? Or if you knew L of 10, could you figure out L of 1/10? Well, let's see. All we have to do is plug 1 over b into the definition of L. So L is the integral from 1 to x. Well, in this case, it's the integral from 1 to 1 over b. And then the rest of this is just unchanged. So if I can figure out what this integral is, I'll know what L of 1 over b is. Well, what I'm going to do for this property and for all of the others is I'm going to do a clever change of variables that lets me figure out what this integral is. Kind of like we were doing on the last test, sort of do a change of variables and get a new integral. So the change of variables I'm going to do here, and as we do some of these, it'll be kind of obvious how I picked it. But now I'm going to let u equal 1 over t. Does that seem like a reasonable change to make? Like 1 over t is what I'm integrating. Okay, well, let's take a differential here. So du is negative 1 over t squared dt. And let's look at my limits, because I have to change those too. If t is 1, then u is just 1. But let's look at my upper limit. If t is 1 over b, what's u? b, right? Because remember, when we do a u substitution, we have to change the function and the d and the limits. So if I plug all this stuff into my integral, I'm going to get the integral from 1 to b of u times dt. Well, I don't know what dt is, but I can move this around and get dt by itself. So dt is going to be negative t squared du. And that's still a little messy because I have a t here. I need to change that into a u. Well, t is just 1 over u, right? So that's negative 1 over u squared du. So that's what I can put here. So it was an easy substitution. I just had to do a little bit of algebra to get everything to cancel out. Any questions up to this point about any of the stuff we substituted? Okay, so now we can simplify. What does my integrand turn into on the inside? Negative 1 over u du, right. which is, I can pull the negative sign out. And haven't we said recently that once I get to this stage, the name of this variable doesn't matter? Right, it's u, I could call it x or q or smiley face. Let's call it t. Now look back at L, capital L. What is this? L of b, negative. So we proved that that equals that. So if L of 10 was 3, then L of a tenth would be negative 3. If L of 100 was 4, then L of 100th would be negative 4. And that kind of makes sense on the graph, doesn't it? Because if you're here at like x, then 1 over x is way over here. And if that's positive, that one's negative. Right? And the bigger this gets, the smaller that gets. So L of b is negative, or L of 1 over b is negative L of b. Questions there? Okay, let's see some more properties. See if this starts to look familiar or even more familiar. So I figured out L of a reciprocal. So if I flip something, what does L do? Now let's see what happens if I multiply two numbers. L of a times b. Now, if you recognize this function or think you recognize it, any ideas what this should be? L of a times b. What do you think it'll end up being? Jed. L of a plus L of b. I think that's a brilliant hypothesis. Let's see if he's right. Okay, well, what's my process? I'm going to write this as an integral, and hopefully I can turn it into the sum of those two integrals. So this is going to be the integral from 1 to what? AB, right? Good. Of 1 over t dt. And now I'm going to do another u substitution. And this is the whole trick, picking the right u substitution. And it turns out for this one, the right u substitution is, well, I kind of want to split this a and b up. So if I divided these limits by b, it would get rid of that product, wouldn't it? It would just turn that into a, and that would turn into 1 over b. So that's what I'm going to let my substitution be. My substitution is going to be take my variable and divide it by b. U equals t over b. Now I know right now what I have written up here is probably kind of hard to wrap your mind around because it's 3 different letters. One of them is a dependent variable, one of them is independent, one of them is a constant. But they all look like lowercase letters. So it's okay if it's kind of hard to see where this is going. But we'll go through it carefully and it'll all make sense. Logan.
How can you just divide it like that? How do you just get t over b?
Logan's question is how can I divide t over b? Well, the short answer is I'm coming up with a substitution. It can be anything that I want. Right? I mean, my substitution could be u equals pi to the t plus 1 power. Like, it can be anything that I want. But we'll see why this substitution actually helps. Okay? Other questions? All right. So let's see what this substitution does. First of all, let's solve for t and take a differential and all that stuff. So t is b times u. And now let's take a differential here, so let's solve for dt. So dt is Now this is tricky, b times u. I mean, it's easy, but it's not easy. Do I need to use product rule on this differential or not? No, because which one of those is a constant? B, so the differential of b times u is just b times du. Exactly, very good. I'll put a little dot there so it's easier to read. dt is b times du. And let's figure out what my limits are going to be. So if t is 1, so let's analyze the limits. If t is 1, then what's u? 1 over b, right, because you just plug it in here. And if t is a times b, what's u? Just a, exactly. And as I look here, I figured out what the limits are. I can figure out what 1 over t is. I have dt in terms of du, so I can do the substitution now and account for everything. So let's do the substitution carefully. It's going to be the integral from 1 over b to a, because I had to change the limits, of 1 over t. Well, 1 over t is 1 over b times u. And dt is b times du. And so I just did the substitution, and now we'll simplify. The b's cancel out, so I get the integral from 1 to b to a of 1 over u du. All right, well, this certainly looks familiar, right? That's 1 over t dt, which is kind of what I hope. But my limits are a little off because this function starts at 1. Well, how can I write this as two integrals that both start at 1? 1 to something of 1 over u du. I think geometrically, like you could figure this out. Okay, so Jed says minus. That might be right depending on what he puts up here. So what's this first limit and what's the second limit? A is the first limit and 1 over b is the next. Good, good. Now let's see, why does that make sense geometrically? Because here you're taking the area between 1 over b and a. Well, here I'm going all the way up to a, and then here I'm going all the way up to 1 over b, and I'm just subtracting the two. It's kind of like when we proved the first fundamental theorem of calculus. I had an integral all the way up to x plus delta x, and one all the way up to x, and the difference, the tail, is just that. So in pictures, if 1 is here and a is here and 1 over b is there. Nope, got it backwards. If a is here and 1 over b is there, then I'm just taking that whole piece minus that piece. And that's what's left. Questions? Okay, now we're almost done. Do you see how this is going to finish up? Because how can I rewrite this first integral?
1 to a 1 over u du plus 1 over b.
Right. I can make this well, yeah. So I can turn it into a plus, but let's do it in this order. Because the integral from 1 to a of 1 over u du is just L of a. And the integral from 1 to 1 over b, 1 over u du, is L of 1 over b. Well, it's not negative, but what do we know about L of 1 over b? It's negative L of b. And that's how I can cancel that negative out. So this is L of A minus L of 1 over b, which is L of A plus L of b, which we will refer to as the Jed hypothesis, and we've now verified it. Okay. So I think if you sat down and had to do this thing from scratch, finding the substitution is the hard part, like figuring out the substitution that works. But if you know what the substitution is, the rest of it's really just straightforward. Like you do the algebra, you do the substitution, you use some properties of integrals here, and you're done. Questions?
I still have a question about
Yeah. Yeah.
How did you do that? Like, I would have never thought to do that.
Well, but now you would because you've seen the proof. And you can watch it over and over again on YouTube until it's just...
But how did you even, how did you do that?
Because I'm kind of guided by this, right? I'm hoping this equals that. If I look at this limit, I'd really just like to have an A in the top there instead of an A times B. So how do I get rid of the B? I divide.
How did I get the 2 of the
Well, I know that that substitution will get rid of the B. Because whatever this substitution is, I have to plug it in
Okay.
to those points.
So it doesn't have anything to do with the 1 over t.
Okay, excellent point. Yeah, for this problem, I'm not really looking at that to get the substitution, which is kind of weird because usually when you're trying to integrate, you look here to get the substitution. But yeah, it has really nothing to do with the integrand. I'm only looking at that upper limit. And that doesn't mean that that's the right substitution, but I hope it is, and then it turned out that it worked. So that's how I know it's the right substitution. Good question. Yes? Would any other substitution work? No, well, you tell me. If you can figure one out, I'll give you 25 bonus points. Absolutely. 1,000. And no, you're not allowed to say 2t over 2b or stuff like that.
Wouldn't dividing by b mess up the value of the bounds?
Well, I changed the bounds. So that's accounted for. And actually, I figured out another substitution that works, so I'm going to take your 2,500 bonus points, so you don't get them. But I do. Sorry. I got it first. What other substitution would work? Yeah, I could divide by A. Right? So you almost had it. You almost had it. Other questions, Madi?
So why did you take 1 over t divided by b? Why was it just t?
You need to think about plugging this in for t.
It's not the entire function. It's just t.
Yeah. Ignore the integrand. Just think about the limit. Other questions? And we have a handful more of these to do, and each one will have a different substitution, so that'll give you a chance to kind of figure it out.
Could you also do 1 over t times a like 1 over t?
I'm not sure if that would work. Basically, you're saying A over T instead of T over A.
Yeah. Well, no, not a over t, but 1 over a times t. Yeah.
I don't know. We could try it. That's a good question. I don't know. 2,500 points if he's... No, I'm sorry. Already recanted that off. But maybe 5. Okay, so let's find some other properties of capital L. What do we think this one is? L of A divided by B. L of A minus L of B. Good. No, actually, this one turns out to be pi. No. No. This one's easy to prove, and we don't have to do any integration to do this one because we already have enough pieces. Because we know how to do a product and we know how to do a reciprocal. Well, if you can do a product and a reciprocal, then you can divide. Because L of A over B is just L of A times 1 over B, which according to my product property is L of A plus L of 1 over B. But according to my reciprocal property, that's L of A minus L of B. So we're done.
So on a test, if that was it, you just write that.
Yes, on a test, if that was it, you could just write that. Okay, one last algebraic property of L. L of A to the B is what? B times L of A. This one we will need to do an integral for, so we'll come up with another substitution. And I'm going to see if you can figure out the right substitution for this one. Okay, so capital L of A to the B is the integral from 1 to A to the B of 1 over t dt. Now, guided by the last couple substitutions that we've done, I want you to take just a minute to think about what would be the right u substitution here, kind of knowing that I might want to end up with something like this. So what does my limit need to be? What does the function need to be? Take about 30 seconds to think it over, talk to a neighbor, see what you come up with. Okay, who wants to give me, u is t, no, t to what? What do I do with t? What's my function? U is t to the b? No? T to the negative b? No? Logan? B root of t. T to the 1 over b. Bye-bye. Now, how do we know, or why do we think this is the right substitution? Because if I apply this substitution to that limit, what does that limit turn into? Just a. So it gets rid of the b, which is what I was trying to do over there. I got rid of multiplication by dividing. Here I'm getting rid of a power by taking a root. So that doesn't mean it's the right substitution, but it means it's logical. So let's see if I can work it out. Yeah? Where does the b go? Well, we'll see, right? Because when I take a differential here, I'm going to be using the power rule, so the b isn't going to completely disappear. So the b will stick around. Okay, so let's say t to the 1 over b. And instead of taking a derivative of that, I'm going to solve for t, just because this is a little bit easier. So t is u to the b. So if I take a differential, dt is, u is a constant. So what's the derivative of u to the b? Exactly, it's power rule. B times u to the b minus 1 du. All right? Yeah, Madi. I didn't hear the question. I just raised everything here to the b power. Madi asked, how did I solve this? And I said, I just raised everything here to the b power. Okay? Now let's do the substitution and see where it goes. Well, my limit when t is 1, what's u? 1. And we already know when t is a to the b, we've already said how that's just going to be a. Now 1 over t is 1 over u to the b. And dt is b times u to the b minus 1 du. Now, the b I can factor out. And if I have u to the b minus 1 over u to the b, I'm just left with 1 over u, because the u to the b cancels out. But now how can I write this? B times what? L of a. Yeah, Logan.
Last step from that to that. Yeah.
From here to here, the u to the b cancels out. So I'm left with u to the negative 1.
What about the du? Is that what you pulled out?
I pulled the b out.
Okay.
I'm left with u to the negative 1. Questions?
So that was like real numbers, like 1 over 4 to the second, and like.
Yeah, it'd be like 1 over 4 cubed times 1 over, no, times 4 squared. Right? There's one more 4 down here.
Makes sense.
There's one more u in the bottom than there is on top. There's one more u in the denominator. Is that the best way to see it?
Yeah.
Okay. One more u in the denominator. It's a lot of letters. It gets hard to keep up with what's important. Other questions about that last line? Okay. So we've proven a times b, a divided by b, 1 over b, and a to the b power, which is pretty much all the properties that we can do now. So let's see what else we can say about this capital L function. We'll just recall that L of 1 is 0. And L of 3, I erased the table over there, but who had that? Who had L of 3 in your group? Do you remember what it was? Or? All right. So L of 3 is approximately that. That was our trapezoid approximation. Or was that the real? Was that the real value? Great, thank you. Now, is L a continuous function? I mean, you've seen the graph, right? It's just, and it's differentiable, right? If it's differentiable everywhere, it's continuous, right? You can't be differentiable unless you're continuous. So L is continuous, at least on 0 to infinity, open interval. So if L is continuous, then I can apply the intermediate value theorem, right? Chapter 1. What does intermediate value theorem say? It says, I'm just going to sketch the graph out here again, so L kind of looks like that. And here it's 0, and here it's 1.09. somewhere L of x has to equal 1, right? By intermediate value theorem. So by IVT, L of C has to equal 1 somewhere. And what does C have to be between based on this picture? 0 and 3. Well, whatever that place is, could you find it, using a calculator, and if you had enough time, could you figure out where the area was 1? You could sort of guess, you could try, you might try like 2.5 and then 2.8 and sort of, it would take a while. Well, I'll do it for you. Turns out that this happens when C equals that value. Does that number look familiar?
E.
That is E. So let's call this E. So by the intermediate value theorem, there is somewhere between 0 and 3 that has an L value of 1. Whatever that number is, we're going to call it E, and that's the definition of E, which you've never seen before. Because it's impossible to define E. Well, it's maybe possible, but certainly not easy to define E without using calculus. So what is E? E is this number. If you take the area under the curve 1 over x, the area under the curve between 1 and E, what does that area equal? 1. That's the definition of E. And that's certainly not the most efficient way of finding E, but that's the way you could find E. You could have your calculator sort of integrate for you and just keep guessing and get closer and closer, and you could finally figure out what E is to a certain number of decimal places. So if L of E is 1, let's use some of our other properties. What's L of E squared? Seems like it should be 2, and if we use my power rule over there, a to the b, the 2 is just going to factor out, so this is 2 times L of E, which is 2. And L of E cubed is just going to be 3, right? In fact, L of E to anything is just anything. So L is starting to look a whole lot like which function? Natural logarithm. So we're not going to say that L is the natural log function because we don't know what the natural log function is. Who knows what the natural log function is? Nobody, because I've never defined it. We're going to say this, the natural log function equals L. So this is the definition of natural log, which again is a function you've been using ever since kindergarten, without knowing any definitions, right, of what ln was. But here it is. This is the definition of ln. And moreover, we have also shown, let me erase a little piece here, that if I define ln to be this capital L function, then the integral from 1 to x of 1 over t dt is ln of x. And furthermore, for that to be the case, the indefinite integral of 1 over x, right, just as a without bounds, the indefinite integral of 1 over x is just ln. Which is the opposite of saying the derivative of ln is 1 over x, which is a formula you memorized back the second week of class. But I never actually had proven that formula for you, and this is the best way to prove the derivative of ln is 1 over x, is because by definition the integral of 1 over x is ln. So it's not a proof as much as it is a definition. Okay? So with that information, we can, and I'll do this next class, I can take a function that's the inverse of capital L. Because think about capital L, it's always increasing, it's 1 to 1, so I can define an inverse function. And we'll figure out properties of the inverse function. And I want to call that inverse function, just to pick an arbitrary letter from the alphabet, I'm going to call it capital E. And we'll see that capital E of a plus b is e of a times e of b. And e of a minus b is e of a divided by a of b. And I'll end up proving that capital E really is just e to the x. And then I'll finally be able to prove something that's fascinating. The derivative of e to the x is, what's the derivative of e to the x? E to the x. And we'll actually finally be able to prove that next class. It's the only function that has that property for real numbers. It equals its own derivative. So to finish up today, I'm just going to show you how to do some simple derivatives and integrals using basically those formulas. And tonight's homework, if you haven't copied it down yet, it's that box up there. But I'll leave that up. Tonight's homework is going to be finding some derivatives and integrals like that. So I'll do a couple for you. Okay, first what I want to do is find the derivative of ln of this horrible looking thing. Now there's two ways you can do it. The way that works and takes forever, and then the way that works and is easy. Which one do you want to try? All right, good choice. So the way that works and takes forever is you're going to say, okay, well, the derivative of ln is just 1 over u, and then chain rule times du. So you'd say, and don't even write this down, it's just going to be 1 over that whole thing times the derivative, right, of that whole thing. And that derivative is going to be messy because it's a product of 3 different things. So what's the clever way of doing this? What should I do first? Separate it. And that review sheet that you did the day that I was sick had a lot of this kind of ln stuff on it. So I'm going to separate the product into this. Just using the properties of natural log, I can write this as ln 4x plus 1, 1/2 of ln x plus 2, and ln of sine of 3x. And now I can take a derivative of each piece separately. This first piece is going to be 1 over 4x plus 1. But don't forget the chain rule, so what do I have to multiply this by? 4. It's easy to forget that piece.
Why is the ln smaller?
Because that's the formula. Derivative of ln x is 1 over x. And then 1/2 times 1 over x plus 2. And this last one is obviously 3 cotangent of 3x. Figure that out.
Cosine 3x over cosine.
Right.
Is that it? Or do we have to add? Is it
Done.
Okay with that.
Easy enough?
Oh wait, this was one of the
So the derivative of ln of sine is cotangent, which we just sort of showed here. So that's interesting because that actually lets us deduce another important rule. What's the integral of cotangent? All right, because I took the derivative of ln of sine and got cotangent. So the integral of cotangent has to be ln of sine. And we'll also be able to figure out what ln of tangent is, too. But I'll do that in just a second. So that's derivatives. Derivatives with ln are pretty straightforward. I mean, if you can do the algebra, you can do it. Integrals can take a little bit more cleverness, so we'll do a couple examples. Okay, write down this integral. The integral of 3x squared over x cubed plus 4. Now, I want to come up with a u substitution to make this work. And you know we're integrating things that look like ln, so we're kind of looking at 1 over x types of integrals. So what should u be?
X cubed plus cube.
Yeah. And let's just see if it works, because du is going to be 3x squared dx, which is a good sign. Because my integral is now just du over u, which is ln of u, which is ln of x cubed plus 4, and then plus c. Here's a little stylistic thing, but it's also important mathematically. Notice how I put parentheses around this, or you could do it this way, x cubed plus 4 in parentheses plus c. The reason is I don't want you to, accidentally think the c is inside of the ln, because that would be a completely different answer. So when you're writing these up, make sure you don't make that mistake. In chapter 6, this will become crucially important because we'll be solving differential equations with ln's and c's. And one of the most common mistakes in chapter 6 is not knowing if that c is added on to the whole function or just part of it. So just start now being really careful about that constant. Questions about that one? Okay, let's try another one. Have room for it right here. I told you we could do this one, so let's. What's the integral of tangent? Well, let's. It's going to be an ln thing. How can I write tangent as something over something? I mean, it's not even a fraction. Right. So let's do that. Because just looking at it, like, that doesn't look like it would be ln of anything because it's not even a fraction. But now this is looking more hopeful. Because if u is cosine, then du negative sine. So if u is cosine x, du is negative sine dx. So this is negative du over u, which is negative ln u, which is negative ln of cosine, plus c, which is also ln of secant, plus c. Why is ln of cosine negative, the same as ln of secant?
It's power, right?
The minus is a power when you bring it inside. Cosine is a negative 1, is 1 over cosine, which is secant. And you will see this integral both ways. I'm pretty sure I've seen it both ways on the BC test. So you just need to be able to go back and forth. Questions? All right, there's one last thing that I want to tack on here, and it's a little strange because I'm not proving this, but I'll prove it next class. Right now, it's just kind of a detail. When you're checking your answers in the back of the book, you will see that all of these ln's are absolute values. And it turns out that that is the formula. The integral of 1 over x is actually ln of absolute value of x. So whenever we do these integrals, they're all absolute values. And it's a minor little detail. I'll show you next class why we have to do that. But I don't worry about it now because you just do the integral and just stick in an absolute value. It always works that way. And it's handy because you can't take ln of a negative number, right? Well, since this is the rule, you don't ever have to worry about if u is negative or not. So you'll see that in the back of the book. And that's it. Homework's on the corner. I'll try to put this on YouTube tonight or tomorrow. Thanks.